For Gauss-Jordan elimination, it's the same thing as Gauss elimination. I just don't stop at row echelon form. I stop at reduced row echelon form. So row echelon form has that lower triangle of zeros. Reduced row echelon form, RREF, looks like this. Where I end up with as close as I can get to identity. And then what conveniently happens is this is my solution. So this here equation tells me that z equals this number. This one tells me that y equals this number. This one tells me that x equals this number. Directly translates to my solution. So in reduced row echelon form, all 0 rows appear last in the matrix. All non-zero rows start with a 1. So 1, 1, 1. You can have additional numbers, and we'll see examples of that. In your REF, you don't always end up with identity, but most of the time you do, for our purposes. When a value of 1 appears in a column, all the other elements in that column are 0. So note there's only a 1 here, only a 1 here, and only a 1 here. Everything else is 0. The first non-zero element of a row appears in a later column, so you get that staircase pattern again. And it turns out that there's multiple REF values for an augmented matrix, but there's only one possible RREF matrix. So everybody should get this exact REF matrix. And we can check in MATLAB what that's going to be using the RREF function. Nice and convenient. So our approach to doing Gauss-Jordan, that's a typo, Jordan elimination, we're going to write the augmented matrix form. We're going to use elementary row operations to transform, just like we did with Gauss elimination. But instead of stopping here at REF, we're also going to make this 0, and this 0. We're going to make all the zeros. And then we can write a solution. So same tips and tricks. Put all the zeros in the first column, then do the second column, and then continue until you get this pattern, until you get all the zeros, until you get the identity pattern. So you just keep going.